Welcome to reInvent. My name is Evgeny Vaganov. I'm a specialist solution architect specializing in networking. This is Net 303 and one of my most favorite topics, shared VPCs. Today I'm going to talk about the lessons learned and the best practices. This is a 300 level session, so I expect to have fair knowledge of the VPC and the AWS networking concepts from the audience. And what are we actually going to cover today? In the next 30 minutes, we're going to talk about VPC sharing. And for folks who are not familiar with it, I'm going to spend just a couple of minutes on covering the basic concepts of that. I'm also going to talk about the architectures that a customer's been implementing when they use the VPC sharing feature. I'm also going to talk about how to achieve network segmentation in the VPC sharing environment. I'm going to talk about how DNS works in shared VPCs. I'm also going to cover the guardrails that you should build as part of your VPC sharing environment, including things like service control policies. And finally, I'm going to talk about perhaps the most frequently asked question to myself. When should you consider using more than one VPC? What are the sizing considerations? And when you should start looking at multiple shared VPCs? So let's start with a quick replay to make sure that we are on the same page about VPC sharing and how does it work. So before VPC sharing, each AWS account had to provision their own VPC, set up all the subnets and all the network resources such as NAT gateways, internet gateways, virtual private gateways, and other. And as you create additional accounts, you'd have to repeat the same process and set it up over and over again. With VPC sharing, it's actually slightly different. We now have an AWS account, which is VPC owner. This account is responsible for setting up the VPC, allocating the slider range, and setting up all the necessary network constructs, such as internet gateway, NAT gateway, route tables, virtual private gateway, and all the subnets. We also have VPC participants. These accounts do not create their own VPC. Instead, VPC owner shares subnets with those accounts. This construct only works within the same AWS organization. VPC owner cannot share their subnet outside of the AWS organization. And in order to do the sharing, we use something called AWS Resource Access Manager. So that's a quick recap on VPC sharing. We have a number of different articles and sessions related to this topic where we explain the benefits of this approach. So I recommend for you to go and check them out if you haven't done so before. Now, let's talk about shared VPC architectures. So the first approach with VPC sharing is that you can create the VPC within the VPC owner account. The VPC owner will set up all the necessary resources at the VPC level, such as VPC endpoints and NAT gateways. And then the VPC owner will create a number of subnets dedicated per VPC participant. So account B, in this case, will have a subnet dedicated for them. They can launch the resources in that subnet. Account C will have their own dedicated subnet created by the VPC owner. They can in turn launch their own resources, and so on and so forth for other accounts. With this approach, the VPC owner has a set of dedicated subnets for the VPC infrastructure level resources, such as NAT gateway and VPC endpoints. And the VPC owner sets up a set of dedicated subnets per participant. If you are following a multi-AZ architecture and utilizing multiple availability zones, the VPC owner will set up a dedicated subnet per AZ and share it with the participant accordingly. So with this approach, we get the best of the both worlds. We get a very strong isolation between the participants because they have their own dedicated subnets, and we also can utilize a shared VPC. The alternative approach to that is where the VPC owner will set up a set of subnets and share them across multiple participants. So in this case, there's a private subnet shared with account B and account C, and they can launch resources into the same subnet. There's another private subnet, which is as well shared with account B and account C. They can launch resources in there. And finally, there's a subnet, which is shared across all participants. With that approach, we can get much better density and utilization of our subnets. But we have increased blast radius. A participant can exhaust all available IP addresses within a subnet and affect another participant. But this architecture only applies to organizations which don't have a lot of spare IP address space, and they must achieve the maximum density in their VPC sharing environment. So let's recap subnet best practices. So the first best practice, we should always monitor for IP address exhaustion. If we don't have any available IP addresses, our VPC participants can suffer downtime and won't be able to launch any new resources. So as a VPC owner, we should implement a way of monitoring a free space within our subnets, free IP addresses. If we need additional density, larger subnets will allow us to increase the density, and sharing subnets across multiple participants further increases the density. But the downside of that is the blast radius. Ideally, we want to have a set of dedicated subnets per participant, so we can reduce the blast radius. This approach will actually help us with network segmentation. If we want to isolate a participant from another participant, we can use network access control lists or network ACLs and isolate one subnet or one participant from another if we have dedicated subnets per participant. Since we started talking about network segmentation, let's continue on with this topic. So first, I want to explain how network segmentation with network ACLs works. So in here we have a VPC owner who has created a number of dedicated subnets per participant. And the VPC owner will provision a number of network ACLs per subnet. So they'll set up network ACLs for the infrastructure subnets. They'll also do the same for the subnets shared with participants. So let's consider a scenario when one of the participants is trying to establish connection to resources of another participant. This might be a valid connection, and that's something that participants might want to allow, but the VPC owner can control and enforce network isolation if they desire so. So in this case, VPC owner can provision a set of network ACL rules and explicitly deny connectivity from the dedicated subnet shared with participant D and connecting into the participant B. So in this case, we just deny the traffic from the entire subnet. Keep in mind that network ACLs are coarse-grained and stateless. What it means is that the number of rules that you can create has to be summarized across the entire IP space. We can't go very specific with the rule set. We're limited to 20 rules, which we can expand and increase up to 40. So the rules have to be coarse-grained, and we have to specify specific network ACL ranges as an example. Now, each participant controls their own security group, so they can, in addition to what VPC owner does, can control access to their own resources. Now, this works for small environments. In the big environments, we need additional network segmentation approach. So let's consider a network segmentation where we perhaps have a much bigger environment. So in this environment, as an example, we have multiple shared VPCs. We have production and not production VPC for internal applications, and they can be in turn shared with the respective VPC participants. We also have a set of shared VPCs for external applications. And again, we have production and non-production. Now we can interconnect them using AWS Transit Gateway. And in there, we can implement a way to segment our shared VPCs with the network appliance. So conceptually, we introduce an inspection VPC. We can deploy a partner network appliance or AWS native managed service, such as AWS Network Firewall, inside this inspection VPC. And then we can use Transit Gateway multiple route table functionality to achieve our business requirements. In this example, production internal can talk to production internal because they are part of the same shared VPC. If we want to talk from production internal to production external, this is where perhaps our business rule says that we must inspect the traffic. And in this case, we can use this approach and send the traffic through the network appliance and only allow the traffic flows that we desire at a very granular level. Production external can talk to production external because they are within the same shared VPC. And finally, if we're talking between environments, for example, from production to non-production, we can black hole or drop that traffic completely and achieve the business requirements with this approach. Now that we talked about network segmentation, let's talk about the guardrails that we as a VPC owners should implement in our shared VPC environment. But first of all, what are the guardrails? Well, guardrails are detective and preventative controls that we set up for ongoing governance of our AWS environment. The first example is preventative. So preventative is where we disable completely ability to deploy certain services. As an example, we might want to disable ability for VPC participants to provision certain resources. As an example, we might want to disable the ability to provision AWS Client VPN, because that might be something that we want to do as a VPC owner and do it centrally. We might also want to disable the ability to expose services to other VPCs through concepts like VPC endpoint services. The other guardrail that we should set up is detective. That's where we can go back in time and retrospectively analyze what's happened inside our environment. A good example of this control is VPC flow logs. Let's take a look of what it looks like in practice. So in practice, for our preventative controls, we can use service control policies. The service control policies allow us to specify the maximum available permission available to our AWS accounts. So we can limit unintended access to different network functions. For example, we can disable ability for VPC participants to provision their own VPC. Therefore, they will be forced to only use subnets shared with them if they want to provision new resources. So let's have a look in this example of our VPC, shared VPC structure. So the first will provision our detective controls, so VPC flow logs, as I mentioned before. We can also provision, launched earlier this year, Route 53 resolver query logs. So we can see all the DNS requests from within our VPC and log them as well. These are two examples of guardrails for our detective controls. Now, we can organize our participants in different organizational units inside AWS organization, and we can configure service control policies to apply to the entire OU. So any new participant will automatically inherit the service control policies provisioned for that OU. Few examples here, we can deny creation of new VPCs, so participants won't be able to create their own VPC. We can deny their use of client VPN, because that might be something that we want to provision as VPC owners and control centrally. We can deny their access to Resource Access Manager, so they can't share their resources to anyone else. And perhaps you want to deny their ability to provision their own DNS. Now, since I mentioned DNS, let's look at how DNS works inside shared VPC environment. So first of all, DNS inside shared VPC environment is very, very simple. The VPC owner creates the DNS configuration, and this is shared consistently across every participant without any further action or configuration. The configuration is completely centralized, so VPC owner owns the configuration of DHCP and Route 53 resolver configuration. It's scalable. Every participant simply inherits the configuration. And finally, participants retain the ability to create their own hosted zones. As an example, they can create a private hosted zone, share the zone with the VPC owner, and a VPC owner can in turn attach or associate that zone with a VPC. So participants can implement their own DNS resolution, which automatically is inherited by every VPC participant, so they can all resolve the same private hosted zone. Let's have a look at how this works in practice. So we have a shared VPC here, shared across a couple of different participants. The VPC owner provisions the shared Route 53 infrastructure, such as inbound and outbound endpoints in Route 53 resolver. The VPC owner configures forwarding rules. In this case, we have a forwarding rule for a domain name that exists in our on-premises environment. A participant attempts to resolve a fully qualified domain name within the on-premises domain name. They'll query the Amazon-provided VPC DNS resolution service that will use the VPC owner configuration provisioned and managed centrally. So in this case, we'll detect that there's a forwarding rule configured for our domain name, and the outbound endpoint configured and provisioned by the VPC owner is used to send that query to our target IP or the DNS resolver that exists in on-premises environment. And finally, the instance in our participant account will get the reply back. And this will be consistent across every participant without any further configuration or a need to share this forwarding rule configuration across our different accounts. Okay, we covered a lot of ground, and finally, I want to talk about the shared VPC sizing configuration. Over many calls I have done with AWS customers over the last 24 months since we released the shared VPC feature, this perhaps been the number one question I heard on customer calls. When should we look at using more than one shared VPC? Can we actually put all of our resources into a single shared VPC environment? Before I answer that question, I just want to remind you that it's the best practice to have more than one VPC regardless of the sizing. You should have a shared VPC for your production environment, you should have another one for non-production, and perhaps another one for a platform development team or network team, so they can actually be able to test network changes without affecting both production and non-production application. Okay, let's take a look now at the sizing configurations. So what I've done here, I built a table. At the first column, I talk about a different scaling factor. So the scaling factor that typically is considered when you think about the scaling of your shared VPC environment. And then I have three more columns. I have the second column where the scaling factor is still within the fine kind of great good to go numbers. So this is where you don't need to talk to AWS to do additional quarter increases, for example. This is where majority of AWS customers perhaps operate. In the third column, the column titled good, this is where with additional quarter increase request, you're still operating within the most percentile of where the customers, AWS customers in the shared VPC environments operate. And in the final column, avoid, this is where you perhaps going to start being outside of the comfort zone where most other customers are, and should look really at setting up more than one shared VPC. This is the time where you also might hit kind of a blocker from AWS where we can't further increase the quota for you. You also might experience some performance issues, and generally just should try avoid being in that bucket. So if you are architecting for shared VPC today, and if you think that you might end up with the number of resources which is close to the avoid bucket, this is a good opportunity for you to think about having more than one shared VPC inside your production and non-production environments. Okay, let's take a look at the first scaling factor, participant accounts per VPC. So if you have up to 100 accounts per VPC, that's great. 1,000, there's lots of AWS customers who are doing that. Once you get to 1,000 plus accounts sharing a single shared VPC, that's a massive blast radius, right? So we would prefer for you to avoid doing that and have more than one shared VPC. Now, the second scaling factor is number of VPC subnets. So up to 200 VPC subnets, that's fine. You can ask for a quota increase and do up to 1,000 subnets per VPC. And again, once you get to that 1,000 plus VPC subnets, the blast radius just gets very, very big. And we recommend for you to consider having more than shared VPC. The other consideration is that once you have a really large number of subnets, the AWS API calls will require pagination. So this way, you can actually get all of your subnets returned in your API calls. The next scaling factor is the number of ENIs, or elastic network interfaces. So 5,000 ENIs, that's within standard quota. You can request a increase of that. Up to 70,000 is still good. At 70,000 of ENIs inside a single shared VPC, you are going to start seeing some performance degradation. And again, just like with other scaling factors, this is a massive blast radius. So think about having more than one shared VPC if you have this many ENIs. Now, to be completely transparent, this affects also peered VPCs. So if you have VPC peering, you should also look at having your overall number of ENIs across all peered VPCs to be under that 70,000 number. And if you need more, use Transit Gateway to interconnect your VPCs and isolate them into different routing domains. The last scaling factor I want to talk about is the number of AWS Hyperplane ENIs. So you might be wondering, what are those Hyperplane ENIs? Well, the Hyperplane ENIs are a special AWS ENI networking construct, which is used by AWS services powered by AWS Hyperplane. As an example is a network load balancer, interface VPC endpoints, elastic file systems, NAT gateways, transit gateways, Lambda, and others. With the nature of the AWS Hyperplane and the high availability of this construct, those ENIs are much more resource expensive. And therefore, the number of those special ENIs that you can provision is less compared to other ENIs. So what is our recommendation? Well, you're fine up until the default service quota. And you should keep in mind that each participant that provisions resources, and resources in turn consume Hyperplane ENIs, will count towards the total number of ENIs consumed. So if different participants consume Hyperplane ENI-enabled resources, that all going to count towards the total number of ENIs that you consume. Additional AZs also consume Hyperplane ENIs. When you have up to 1,000 Hyperplane ENIs, you're still in a good bucket. And if you expect to consume more than 1,000 Hyperplane ENIs, you should really consider having more than one shared VPC connected together with transit gateway. All right, with that, I'd like to summarize what we've learned today during this session. First, VPC sharing allows us to share a VPC amongst multiple AWS accounts within the same AWS organization. There are many AWS users who successfully deployed shared VPCs in production. The way they've done it, they typically deployed shared VPCs side by side with their existing environment. They interconnected them using VPC peering or transit gateways and migrated over time. Some of those VPCs run at a very large scale. We talk about the best practices with the architecture and how we can use guardrails in our VPC sharing environment. And finally, we talked about scale. We talked about the different scaling factors and when you should look at more than one VPC in your environment and have them interconnected with transit gateway. All in all, to summarize, VPC sharing is a powerful tool for cloud networking. You should consider using it in your environment because it gives you many benefits of avoiding duplication of resources, cost savings, and also ability to preserve IP addresses. Thank you very much for dialing in and listening to me today. Please leave comments and feedback and complete the session survey. Thank you very much. Enjoy the rest of your reInvent.